Hi everybody, welcome to our second to last video in this series of probability videos. You're almost at the end, congratulations. This video is going to be a little bit shorter than some of the other ones, I think, because this video is just on one topic, on a topic called tree diagrams. So I'm going to tell you a little bit about what tree diagrams are, what we use them for in probability, and then we're going to do some example problems here, okay? So tree diagrams are called tree diagrams because they literally look like trees and they have these things called branches on them. Okay. So like on the left side of my screen, I give you a picture of what a tree diagram looks like. It's basically what happens when you start somewhere and then make a decision, and then that leads you down a path, right? And then maybe you make another decision, and so you go down another path off of that. So there's lots of different options that branch off when you make more choices. So what we use them for typically in probability problems is we want to see that maybe all of the outcomes of an experiment, or when you're making choices, and you want to see how those choices pan out. So you make one decision and then the next and then the next and then the next. It allows us to visualize things that happen one after the other. So like we've been dealing with two-way tables and Venn diagrams. That doesn't really tell us anything about, or not much of anything about, if we choose one thing and then we choose another thing. It's just giving us an overview of the probabilities of certain events and how they're related to each other. Tree diagrams are great when you're talking about making choices or doing one thing after the other. Okay, so on a tree diagram, we are still dealing with events and how those things are related to each other. So like, remember at a Venn diagram, you have two events and they overlap like this, right? And you have the intersection in the middle, and you have an event here and an event here. In a tree diagram, each branch of the tree is an event. So if you look at my very fancy tree diagram that I have on the right side of the screen, actually I can help you visualize it. So each of these branches, so like this line and this line, those are branches and they represent a choice. So this first group is like the first choice that you would make. So if I start here, I make this choice, then I arrive at this set right here. And then say I make this choice, and then I arrive at this third set, and then maybe I make this choice after that. Okay. Right. So when you go through each level, you make a choice and then it leads you to the next level or the next choice that you're going to make. Okay. So one of the key things about tree diagrams is that each of these groups of branches has to add up to 1 or 100%. And I'm hoping that by now, if you've watched all of these probability videos, that you have an idea as to why that is, right? If I have two choices, right, those represent the entirety of the possibilities that I could make, right? Or that could happen, right? I either make this choice or this choice. It's 100% of my total choices that I'm holding here in my hands, right? So these two things that I'm deciding between are like the two branches on a level of a tree diagram, right? And tree diagrams don't have to just be two choices, right? You could have 3 or 4 or 5. You could have an endless number of choices at each level, but you know you can only pick one and then go on. So altogether, the bunches have to add up to 1 or like 100%. So before I can do anything with a tree diagram, it has to be complete, right? Like I have to have a complete tree diagram. So in this problem, we're going to be pretending that we're going to an ice cream shop, right? So I don't know about you, but that was always one of my favorite things to do when I was a kid, like in the summer is, and we wouldn't do it very often. It was this like rare treat that we got to go to, one of those fancy ice cream places where they like, you pick your ice cream and you pick like 2 toppings to go in it. And then they use the spoons and like mix it all together. And then you get to pick your cone and stuff. It was always my fave when I was a kid. So that's kind of what we're doing with this tree diagram. So we're going to make an ice cream choice, or rather we're going to make a cone choice, and then an ice cream choice, and then a topping choice. Okay, so we are going to make those choices like one after the other. So a tree diagram is perfect here. Okay, so I know a couple of probabilities and I wrote them up for you at the top. Okay, so like I know that in this shop that the probability that I'll choose a waffle cone is 0.4, right? So that's what this is right here. Then I know that the probability that I'm going to get chocolate ice cream if I get a waffle cone is 0.55. So that's why I have this 0.55 up here, right? So I've chosen a waffle cone, and then after that, I chose chocolate. So that's the probability of chocolate given that I already chose a waffle cone, which kind of makes sense, right? Because then if you look at the other cone, right? So the probability that I get chocolate ice cream if I order a dipped cone is different, right? Because it's a conditional probability, right? So this choice that I made first is affecting the choices that I made later. Okay. And that doesn't always happen in tree diagrams. Sometimes the first choice that you make doesn't affect the next choice that you make, but in this scenario we're gonna assume that it does. Okay. Right? And then I have these other probabilities that remain the same no matter what choice I make, right? So like see how here in the third level that the probability that I get chocolate fudge and the probability that I order strawberry syrup is the same for all of these, no matter which ice cream choice I made, no matter which waffle or which cone choice I made. Okay. So what I want you to do here is take a couple of minutes and see if you can fill in the blank spaces in this tree diagram. So I'm going to give you an example first to show you how to do it, and then I want you to pause the video and try it. So here, I'm going to focus on this first level right here. This is my cone choice. So I'm either going to pick a waffle cone or a chocolate dipped cone. And I know that these all together, this has to add up to 100%. Okay, so if this one is 0.4, right, or you could think of it as 1, right? This is 0.4, then that means this value right here has to be 1 minus 0.4, or 100% minus 40%, which is 0.6. So that missing value there is 0.6, right? So I want you to give it a try and see if you can fill in these other missing values. What I want to note for you is that this bunch, on the third level, is this, you're going to get the same number in all 4 of these boxes, okay? So give it a try and then come back and check it with me in just a minute. Alrighty, so check your answers against mine. So I got 0.45 for this top vanilla value. So I did 1 minus 0.55 to get that. I got 0.61 for the bottom tier of the bottom cluster of branches for that second level. So notice again that these two values, when I add them together, give me 1 or 100%. And then you got 0.43 for the Oreo probability, okay? So now that we have our tree diagram filled in, let's use it to figure out some probabilities, okay? So let's look at part A here. So this says represent probability of D, which is this guy right here, the dipped cone, using complement notation. So I know it's been a minute since you've seen the word complement, but remember, complement means not. And you've actually been using it already to figure out what these missing probabilities are. You maybe just didn't recognize it or make the connection because you did 1 minus something to get something else, right? So probability of D, oh dear, my thing has decided to stop cooperating. Give me just a second. I have to fix this. Stand by. Okay, sorry about that, everybody. So complement notation. Complement notation is always going to be the probability of something, so the probability of D, is equal to, it's 1 minus the probability of something else. And my only possibility here for this probability notation, the only other option in this tier is W, right? So probability of D is equal to 1 minus the probability of W, which is exactly what we did when I did the example in order to help you figure out what this probability was, okay? All right, so let's look at part B here. It says, what is the probability that you don't order a waffle cone? Well, that's this up here. It's the same thing as part A, right? Because if I don't order a waffle cone, my only other choice is to order a chocolate dipped cone. So that is the probability of D, which we already found is 0.6, okay? All right. Let's look at part C. This says, if you order a dipped cone, what's the probability that you'll order vanilla ice cream? So I already know that I've ordered a dipped cone. So if I start here, I already know I'm going down and following this branch. Okay, so this is a conditional probability. What I'm trying to find here is what's the probability that I get vanilla ice cream given that I already know I'm getting a dipped cone, which we already calculated right here. So that probability is 0.61. Okay. All right. Part D. Now, this is the tricky part and one of the key things that you need to know about tree diagrams. Tree diagrams represent events that are independent of one another, right? So we're assuming that like this choice that I make doesn't necessarily affect the next choice or the probability in the next tier and the next tier and the next tier. So if you remember from the last video, when we're talking about and probabilities with independent events, you can multiply the probabilities and it will of the individual events, and it will give you the and probability. So in part D, this says, what's the probability that you order a chocolate dipped cone and vanilla? Okay, so what I'm going to do is I'm going to follow my path that's stated for me in the problem, and I'm going to multiply along the branches that I follow. So I'm ordering a chocolate dipped cone. Okay, so that's the 0.6 probability right there, and vanilla. So I'm going to figure out what this value is, the and probability, by multiplying these two numbers together, 0.6 times 0.61. So let's do that. So the probability of dipped and vanilla is 0.6 times 0.61. So remember, this is the multiplication rule from the last video. So let's pull out a calculator and figure out what that is. So 0.6 times 0.61 is 0.366. Okay? And the more choices that you make, right, the further along the diagram you go, the smaller these probabilities are going to get, right? Because you're multiplying by decimals, right? So when you multiply a decimal by another decimal, it keeps getting smaller, right? And I'm hoping that like instinctually that kind of makes sense, right? Because if I make more choices and I have more possible outcomes, then the probability of each of those individual outcomes has to be a little bit smaller so that I can accommodate for more options and for more combinations of things, or in this case, more combinations of ice cream cones. Because in the end, I know that the probability of all of my choices together, all of my possible combinations, is always going to be 1 or 100%, right? Okay, so there's two other questions here that deal with this tree diagram. So I want you to try those. Okay, so the first one says, what's the probability that you order a vanilla cone with Oreo cookies and a waffle cone? So this is an and probability. So you're gonna have to do some multiplying. And then F is build your own ice cream cone Obviously, I won't be able to give you the answer for that one, but try that one as well to get some practice with multiplying. All right. So pause the video, try those two, and then check back with me in a second to check your answer, at least for part E. All right, welcome back. I'm hoping that you got the same answer that I did for part E. So we're finding this and probability. I want a vanilla ice cream cone with Oreo cookies in a waffle cone. So that's waffle and vanilla and Oreo. So I've got three paths I have to, three branches, three levels that I have to follow. So I'm going waffle, so that's 0.4. And then I multiply along the branch. So vanilla comes next, so times 0.45, and then times Oreo, which is 0.43. Okay. If you want me to check if you did part F and you built your own ice cream cone and you're not sure if your answer is right, just send me a message and I can check it for you. All right. So there's one other type of problem that typically shows up with tree diagrams. So give me a second to clear my screen and reset some stuff, and then we're going to do one other example with tree diagrams. See you in a second. All right, so here we go. Last example with tree diagrams. So for this one, we're only going to focus on the first two levels because when you add the third one, it gets a little bit crazy. So we're just going to focus on the first two levels, which was my waffle cone, my dipped cones, my cone choice, and my ice cream choice. All I know when I go into this ice cream shop is that I want chocolate ice cream. That sounds so good right now. I just want some chocolate ice cream. So I want to figure out, okay, what are the different ways that I could order chocolate ice cream? Okay, so let's think about that. What are the different ways that you could order or not you, me, because I'm in the ice cream shop. So there's lots of different ways that I could order chocolate ice cream, right? I could order chocolate ice cream with a waffle cone, right? Or I could order chocolate ice cream with a dipped cone. Right? Those are my only two options, right? Because remember, the only thing I care about is that I get C, this chocolate ice cream. Okay. So a common question that will be asked when you're talking about tree diagrams is, okay, well, what if I don't care about the cone and I just want to know what the probability is that I order chocolate ice cream, right? So like maybe I'm the person who owns the ice cream shop and I'm trying to figure out, okay, how much of each ice cream should I order or make so that I have enough of the really popular flavors for people and maybe not make as much of the stuff that's not as popular, right? So I get all these probabilities and then I figure out how likely it is that people are going to come in and order a specific type of ice cream, okay? So the probability that I order chocolate ice cream changes depending on which cone I choose, right? So what they've seen is that when people order a waffle cone, the chance that they're going to order chocolate ice cream with that is 55%. But when they order a dipped cone, the probability that they're going to order chocolate ice cream with that is only 39%, right? So what we're going to try to do here is figure out what's the total probability that I order chocolate ice cream, okay? So what I need to do is figure out, okay, what's the individual probabilities? What are the individual probabilities of this option and this option, right? So I need to follow this path, right? Because that path leads me to chocolate ice cream. And I need to follow this path. And since both paths lead to chocolate ice cream, I need to add them together at the end. Okay, so let's do that. So the probability that I order chocolate ice cream is equal to, I need to add both of my paths, right, that lead me to chocolate ice cream. So I need the probability of, oops, let me erase that. That's the wrong letter there. So what's the probability that I order chocolate ice cream given that I ordered a waffle cone? And then I need to add what's the probability that I order chocolate ice cream given that I'm going to order a dipped cone. Okay, so C given W is this first path up here. So this is C given W. Okay, that's my top path. And this one down here is C given D. So let's figure out what those two probabilities are by doing some multiplying. So I have 0.4 times 0.55. And then I need to add, so that's his first path, and then I need to add 0.6 times 0.39. Okay, so I'm going to give you a second, pause the video, see if you can figure out what that probability is. All right, so I finished working that probability problem out, did some multiplying and adding, and I got 0.454. So I'm hoping that you got the same thing, okay? So the last question that I have on this one is, okay, if I'm craving chocolate ice cream and my friend that comes with me just wants vanilla ice cream. So the question is, how could we figure out what the probability of vanilla ice cream is, the total probability? So we could absolutely do the same thing that we just did, right? So I could say, well, what are the paths that lead me to vanilla, right? So I could follow this path that leads me to vanilla, and then I could follow this path, right? Those lead me to vanilla. And I could do the exact same thing that I did up here, right? Work those probabilities out. But I also know that there's only two ice cream options, right? I either order chocolate or I order vanilla. So I can use the complement rule if you want, or if I want to. It's a little bit less math, and maybe a little bit simpler than doing all this multiplying. So I know that the probability that I order vanilla ice cream has to be 1 minus the probability that I order chocolate ice cream. So even though I can order vanilla ice cream in multiple different ways, that doesn't matter, right? If I'm talking about ice cream choice, I only have two. So we know that chocolate plus vanilla together has to add up to 1, just like it did at each of the individual branches, okay? So I can just do some subtracting here. So vanilla equals 1 minus 0.454, because that's what we found up here. This 0.454 is the probability of chocolate, okay? And so when I do that, I get 0.546, so 54.6% that I order vanilla ice cream, okay? So that's pretty much it for tree diagrams. If you want to try number 3 on there, you can. One thing that I will point out to you about number 3, typically I would go around the classroom and I would give you, I would give every table a different, like, really long word, and you would have to pretend that you cut all of the letters in the word up and threw them into a hat, and then tried to figure out what your choices would be, like if you drew letters out of the hat. So, like, say, I don't know, I'm gonna pick a word at random. So I don't know if you all know what this word is, facetious. So facetious means like sarcastic, and it's actually one of the only words, I think it might be the only word in the English language that has all 5 vowels in alphabetical order. A, E, I, O, U. That's why I like it. It's a fun word. Okay, so if I was to chop up these letters, right? So here's my letters, and put them into a hat, I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. And then say I wanted to figure out what the probability was that I drew a vowel, right? So say I'm doing this one, consonants versus vowels. So C and V, and I'm trying to figure out what the probability is at each turn. Okay, so the one thing that's a little bit different about this tree diagram than the one that we did up at the top and that I've done in the previous part of this video is that we're doing and picking these letters out of a hat, but we're not going to put them back in the hat when we're done. So the choice that I make in the first tier, like the first letter that I pull, after I take that letter out and it's not an option anymore, it's going to change what the probabilities are going forward, because I took something out of the hat and I didn't put it back. That's called doing something without replacement, literally not replacing it, not putting it back. So I want to show you what I mean, and then you can try this if you want, like maybe pick a dictionary or like just get a random word out of the dictionary and see if you can do these probabilities. So here in my original word, I need to figure out, okay, how many vowels do I have? So I have 1, 2, 3, 4, 5 vowels. So 5 out of 9 of these original letters are vowels, and the remaining 4, so 4 out of 9 are consonants, right? Simple enough, right? So let's say I chose a consonant on the first one. Like my very first draw was a consonant. So say it was this S and I'm getting rid of it. Okay. So now I have to ask myself, okay, how many letters are left? Right? If I get rid of the S, there's 8 letters left. Right? So instead of taking these out of 9, I'm taking it out of 8 because I drew a letter and I didn't put it back and there's only 8 left. So now I have to look at, okay, how many consonants are left here? If I took out the S, there's only 3 consonants left. This one, F, C, and T. So there's only 3 consonants left, but there's still 5 vowels, right? Okay, the A, E, the I, the O, and the U. Okay. But, okay, so let's go back and say, well, what if I drew a vowel first? Right. So let me do some erasing here. So let's say I drew a vowel first. Right. Maybe I drew this E right here. Okay, so let's say I drew the E. So then I need to ask myself, how many vowels do I have left? Well, I still have the A, the I, the O, and the U. So there's only 4 vowels left. And there's 8 letters, right? Because I took the E and I removed it from the hat. And I didn't draw a consonant, so there's still 4 consonants left. And you could keep going with those probabilities, okay? So this is another way that tree diagrams are used and how you can see how like one choice affects the probability of other choices that you make. All right. So the very last video in this series is on geometric probability. So that's going to combine all of the stuff that we did with area and combine it with these probability ideas. All right. So I will see you in the next one. Bye, guys.